Okay. Okay. Well, thank you very much, Ron. Again, my name is Dave Rosado with Harley Thermal. I'd like to thank everybody for taking the time out this morning to attend the presentation. I also want to thank Glenn Research Center and the TFAWS organizers for making this virtual conference possible. Okay. 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 What I'd like to start is with the software. What you're seeing here on the screen is our Solaria product. Solaria is a general purpose thermal simulation tool. And what we also have is a front end to Solaria, which is called Solaria PCB. And I'll switch to that. Okay, so I've switched to Solaria PCB, and that activates this menu over here. And what we're going to do is going to start out by importing an ECAD file through an ODB++ file. So I'm going to click on PCB and then import ODB++. Most ECAD tools like Mentor, Cadence, Zuken can all write out an ODB++ file. It's a single file, has a TGZ extension on it, and it's a compressed file. But the nice thing about it, it contains everything about the board. It contains the layers, the board shape, the components, all the traces and vias and everything on every layer. So it's an easy way of getting all the information we need to do a complete thermal simulation. There's a couple of options in here. It says a number of segments in a circle. When you bring in an arc or a circle from an ODB++ file, we convert it into segments. This defines whether it's 4 segments or 6 or 8. Now we recommend 4 because a square hole compared to a round hole thermally isn't that much of a difference. I'm going to be working with inches this morning. So I'm going to come over here and select my TGZ file, and it read the file and tells me we've got 9 layers, and these are all the different files that were created by expanding this TGZ file. So I'll hit the import button. And this is just one note saying it found a layer that didn't have any traces on it. So we'll take a look at that. Okay, so there was 122 components on the board. That's different components, and there's 1,269 placed components and 2,582 vias. So all of that was imported. Okay, so I'm going to hit the cancel button since it's all done. Now what comes up next is a mapping dialog, and this is on the left side are all the components on the board we just brought in, and on the right side is the component library that comes with Solaria PCB. Okay, the idea here is to pick a component on the left side on your board and try to find a matching one in the library. Now I'm going to hold off on going through this right now because I want to show some other options as well first. So I'm going to hit cancel here. Okay, so there's the board that was just imported. So this is the printed circuit board. You see there's a lot of complexity to it. So let's take a look at what was imported. So we'll first go down to PCB outline. So this data here defines the shape of the board. So that's imported. Now we'll go down to layers in the board. So these are all the layers that were imported, okay? And that dialog, that message that came up during the import was because this layer here didn't have any metal layers on it. So that's why it was checked here. Now, what we're going to do with this board is we're going to add an aluminum plate to the back of it, bond an aluminum plate to the back of it, and extend the aluminum plate out to hold wedge locking devices. And the wedge locking devices in a typical application will clamp it to a heat sink sidewall. So I'm going to hit the add layer twice, and I'm going to add a bond material, and I'm going to add a heat sink material. Okay, and I'll make the bond 10 mils thick, and I'll make the aluminum 60 mils thick. Now the type of layers I want to create are 3D layers, and this means when the Solaria model is created of this board, they're going to be three-dimensional elements, so it'll account for heat transfer in all directions. And that's important for a bond to make sure we get the gradient through the thickness. Now for a material, it comes with a material library, so I'll just pick a typical bond material. And our heat sink is made out of aluminum, so I'll select aluminum. There's a very complete material library that comes with Solaria, and you can add to it as well. Okay, so there we have it. We have our layers defined, and you can see all the thicknesses and the names all come in from the ODB++ file. If you're not using FR4 and you're using G10, then you can come over here and you can click on Update Materials, and it'll redefine, and as you can see, it redefined my layers I just added, and I'll just quickly put those back in. Okay. Add my bond material and my aluminum again, and we're all set there. Okay, so let's take a look at what else is on the board here. You can see there's a lot of artwork and everything. So I'm going to hit the clear button here in my View Entities dialog, and I can come over here and look at each layer one at a time. So you can see there's a lot of complexity, and all of this information, whether it's a signal layer like this one here, or possibly a power or ground plane like this one here, all these layers come in and all the definition. If I turn on vias, so we can look at the vias that were imported, if I look close, you can see some of the vias are inside a hole and some aren't inside the hole. So we know exactly what layers each via is connected to, electrically and thermally. When it's in a hole like this, it's sort of isolated thermally as well as electrically, and we account for that in the simulation. So we have all of that information available to us, and that's the advantage in importing an ODB++ file. When you're doing a simulation and you're required, and your design is utilizing the board as a conductive path, it's important to accurately simulate it. Okay, so let's take a look at all the components. And again, we had over 1,200 components imported. Now, we really don't want to model every single one of them. Typically, ICs are the important ones. So what we want to do is, from these here, we want to segregate out just the important ones, the ones we want to take some time to calculate junction temperatures for. Okay, so I'm going to hit OK here, and I'm going to go to PCB, down to Define Active Components. So an active component is what we're classifying as a component that we are going to simulate and calculate junction temperatures for. Okay, so all the resistors or capacitors or something we're going to neglect unless they have dissipation. If a resistor does have some dissipation and it's not active, well, that heat will be added to the board at the location of the resistor on the appropriate side of the board. So that's all done automatically. Now what we have here, if we come in here and let's say we want to set ICs as being active. Okay, so we can just click on ICs and hit the Set Active button. Okay, and oops, sorry, and you'll see just ICs are active. All the ones down below, the capacitors and everything else, are not checked. Okay, and you can see on the screen only the ICs are visible. Now you'll also notice that all these blocks are red. Now there can be 3 different colors: red, yellow, or green. Red means there isn't enough information defined yet to do a thermal simulation of that component. Okay, yellow means there's enough information to simulate the component, but there is still some missing information. And green means everything's there. Okay, and that's what we're striving for. So if I click this button here, okay, this is where we define what type of component it is. If it's a BGA, we'll come down and select what the BGA solder balls are made out of. And then we go into geometry, and now we need to complete the rest of the information in here that's missing. Okay, so this is what needs to be done, and the reason is because Solari is going to calculate the the resistance between the case of the component and the board for you. So it's going to do that based on the lead geometry and material for a leaded part, or if it's a leadless part, a surface mount part, it'll be based on the pad geometry and material. If we hit thermal properties button here, okay, this is where you define the internal representation of the component itself. It can be as simple as a case node, where we can just add a node here, and the software will create the connection between the case node and the board based on the geometry we just looked at. Okay, so all of this needs to be done for each of the components. Okay, now I spent the time to go through that. Okay, and one of the options in Solaria is to export a component file. Okay, and what a component file is, let me bring it up here. Okay, what we're looking at is Excel, and this is all this data here was all exported after I had defined the geometry and the thermal information for the different components, all the ICs on this particular board. Okay, so I can import this file into Solari PCB and define all that information. So that's one way of doing it. So if I go back into Solaria PCB and I go PCB component file, then import, and I'll select the CSV file. So from Excel, I saved it as a comma separated file, and then I'll open it. So it defined the components, or 37 different components. Okay, so now if we go back into the define active component dialog, you'll see everything is green because all the information in that for these components was in that file. Now there's a few of them that didn't have any dissipation, and that's why they're red. So I can come over here and sort of deactivate those. Okay, so now everything that is important is green, and it is one here that dissipates some heat, and it's active. So we'll set that as active as well. So that's the goal, is to define the geometry and define the thermal information for the components. Now, another option, once you've done that for this board, what you'll want to do is save that information to the library, the component library. So the next time you do a board, if some of these components are on the next board you do, you could take advantage that they're in the library now, and you can use that mapping dialog. So let's bring that up again. So if we go PCB and then map components, okay, again, this is the dialog that came up just after we imported the ODB++ file. Okay, so if we use this auto search feature, okay, it'll go through each of the components on the board I just imported, okay, and look for a match in the library. Now I've already done this. I've saved the components to the library, so you can see it's finding matches for all of these. Okay, and by hitting yes, it's taking the information that was created before and defining it in the board I'm working on now. So it's found 16 matches. Okay, so to do that, if you go to PCB and then add components to lib, this is where you'd select those components, and I can check active only here. So these are the ones I spent the time to define the geometry and the thermal information for. So I can click on all of those, hold the shift button down, highlight them all, and then hit the left arrow button. And that'll send the components and put them in the master component library, again, so they're available for the next time you do a board. You won't have to define those components. So the more you use the software, the less of this tedious stuff that needs to be done. Whether you're doing a board manually or using any other software, this is probably the most tedious thing of the whole process. The advantage in Solari PCB is that it's bringing in all this stuff, so you don't have to define the layers, you don't have to define the component placements and everything, so you really can concentrate on defining the components themselves. Okay, so we've got components, our components are defined, our layers are defined, and we have dissipation, so now we've got to define our heat sinks. So let's go into PCB and then add, we have an option called define wedge lock edge. Okay, so here's a cross view of our board. If you recall, in the layers dialog, we added a bond to the back of the board, and then we bonded an aluminum plate to the back of the board. Now, that aluminum plate is the exact shape of the board, but we want to extend it out as shown in the picture here. Okay, so I'm going to click on this here. I'm going to click on define edge temperature, and from a previous analysis, I've calculated that the left side will be at 60 degrees and the right side will be at 50 degrees C. Okay. The resistance of the wedge locking device is 0.3 degrees C per watt. And then based on this geometry over here, the extension width is 0.44 inches. The wedge lock itself width is 1/4 of an inch. The wedge lock is 5.5 inches long, and the distance from the bottom is 1/4 of an inch. Okay, and the layer in the model, you notice only 3D layers show up here. This is the heatsink, aluminum heatsink that I added to the back of the board, and that's going to be the one that's going to be extended out to create the wedge locking device. And I also want to say that the contact is on the front side of the board. Okay, so when I hit OK, you notice it doesn't show up on the screen yet, and that's good. When I go back to PCB view entities, I had contacts turned off, and there they are. There's my wedge locks. So they extend out on the left side and the right side, and there's my contact area. Okay. Okay, so I have a complete board in that short amount of time. I was imported the ODB++ file. I defined my layers. I added the aluminum plate and the bond, and I added my wedge locks, which defines boundary conditions. Okay, so what I'm going to do is I'm going to go PCB, save as. I'm going to call this PCB. I'll just give it a name. Okay. Okay, so we're all set. We have everything defined, and that's ready to create a Solari model. So I'm going to go to PCB and then build board model. Okay, and then I'm going to just hit build. Okay, so it just meshed the board based on all the geometry we see on the screen, the component outlines and everything. It created a 2D mesh, a triangular mesh of the board. It's a Delaunay mesher, creates triangular elements. And what it's now doing is going through each layer of the board. And here you can see it was on layer 1, now it's on layer 3, and there's 6,552 triangles in the mesh, and it's going through each triangle and looking to see how much copper is, or if a trace is passing through that triangle, or if there's copper in that triangle with holes in it and stuff. And it's thermally representing what's in that triangle with 3 resistors that go in the 3 corners of that particular resistor. That's doing that for every single layer. You see, some go quicker than others because their different layers are more complex than others. Okay, so it's building the complete board model now, and when it's done here, you can see this one's a little bit slower. Layer 17 was a little more complex, so it just takes a little bit longer. And then what it'll do, it'll go through the vias. There it is now. It'll go through the 2,500 vias and represent them as resistors going through the thickness of the board. And it knows which layers they're connected to. So it's going to make the thermal connection for each triangle where all the vias are, very specifically. So I'm going to hit apply here. It gave me an option to offset the model, but we don't need to right now. And it's cleaning up the model right now, and it's all set. So let's hit cancel here. Now, if I select this button here, this is how we got into PCB mode. If I click on it, we go back to Solaria mode. Okay, so this was the model that was just created of this board. Okay, you can see all the triangles. If I close in a little bit closer, these are all the triangles I was talking about, the 6,500 triangles. And each one of them, again, has resistors going each way at each different layer of the board. Again, it's a full 3D model. So if there's 10 metal layers, there's going to be 10 nodes through the thickness of the board. Okay. If I look at a side view, okay, and zoom in a little bit, you can see there's a bunch of nodes. If I click on this button here, I can query. So if I hit select and click on one of these, okay, there's a nodal heat load there, okay, and it references property 20, and the name of property 20 is I18, and it has a value of 0.9 watts, okay. If I click the little resistor, the little line right below it, that's a resistor element, and that represents the junction to case that I had defined, the junction to case resistance. And again, that also references property 20, and it has a resistance of 3.4. Again, that's exactly the numbers I put in the in Solaria PCB. So if I go into the property table and go to number 20, so here's I18. Again, every component, every active component I've defined references its own property. So I can come in here. If later on the resistance, changes or something, I can come in and change it without having to go back to Solaria PCB and rebuild the board. The dissipation is here, 0.9 watts. And I can change that if I wanted to as well and do another simulation and run it again. If I go back to the beginning here, each layer references its own property. So if I'm running too hot, and I look at the gradients in the board, they're excessive, I can try 2-ounce copper instead of 1-ounce copper by just changing the thickness here. Again, I don't have to go back into Solaria PCB, define it there, and then rebuild the board. You can do it right in here. And here's the left wedge lock and the right wedge lock. You can see they have their own property as well. The heat transfer, the 0.3 degrees C per watt was converted to a contact coefficient of 2.42 based on the 0.3 degrees C per watt and the area of the wedge lock. There's a question that came up. Does a software package allow for simulation of cooling solutions in addition to just PC boards? The environment we're in right now is Solaria. Solaria is totally a general purpose thermal simulation tool for doing transients, steady state solutions. There's thermostats, there's all different element types. We can import CAD, which we're going to do a little later on this morning as well. So it's totally general purpose software. Solaria PCB, where we started out, is a front end to Solaria just for creating the models we're looking at right now. Okay. Let me close all these things here, and we're all set to solve. Okay, we really didn't have to do anything to the model. So I'm just going to hit the solve button here. We have two solvers. One's a funny different solver, and one's a conjugate gradient solver, and that's the one we're using right now. Okay, you can see it's solved within 5 seconds. Okay, the number of resistors in the solution were 150,000 resistors in the solution, and there's 26.42 watts in the model. Okay, so you can see, even though it was a pretty complex board, again, the full 3D model still solves pretty quickly. in Solaria. Okay, so let's take a look at the results. Okay, so here's the temperatures. We have 131 peak. And if we want to look at the component temperatures, we can go to results and then PCB results. Okay, so here's a listing of all the active components. We have a junction and a case temperature. Okay, here's the dissipation that was defined. Okay, and we also have a local board temperature for every single component on the board, whether it's active or not. Because sometimes for stress sheets, or you've got to report, the operating temperature for the resistors and the capacitors. The capacitors got to keep below a certain rating as well. And then the case to board resistance. That's the resistance that was calculated based on the lead or solder ball or the pad geometry. So these are calculated values, and we report them back to you, so you get to know, you know exactly what they are. Okay, and then the junction and case is given, and that was defined in the thermal properties dialog we brought up. Okay. Okay. Now another thing I want to note is, one side of the board had a boundary temperature of 60 degrees, and the other side had the boundary temperature of 50 degrees. So what I've just done is now we're just looking at boundary nodes on the two sides. And if we want to see, how much heat's going out one way and how much heat's going out the other way, we can go into our solution data here, hit this calculate button, and then I can box in all these nodes, and I can box in all these nodes. So I've got 15.06 watts going out one side, and I've got 11.36 watts going out the other side. Okay, so that kind of information is important if you're iterating in your system model. You may want to update it to give it more accurate numbers for how much heat's going out the two sides of the board. Okay, so there's a lot of capabilities in Solaria for doing post-processing and looking at the results and plotting transients and everything. So it's a very capable, very complete tool for doing just general purpose thermal simulation. Okay. Now what I'm going to do is I'm going to come up here and I'll turn everything back on. And I'm going to actually clear this model. Okay, I'm going to hit this button here and just trash it. Because what I want to do next is I'm going to import a step file of an enclosure, and then I'm going to put that board inside the box. Okay, so what I'm going to do is I'm going to bring up it's a shareware 3D meshing tool called Gmesh. And what I'm going to do is I'm going to go File, Open, and I'm going to select the step file. Okay, here's the step file. And I'm going to import it. It's a very simple box. Okay, it's got two card guides. So you can have one board that goes up against this card guide and another board that goes up against this card guide. Okay, so what I'm going to do is I'm going to click on Mesh, and I'm going to click on 3D. So there's a pretty straightforward 3D mesh that looks a little coarse, so I'm going to refine it by hitting this button here. Okay, so there's what I'm deeming as an acceptable three-dimensional mesh that was all meshed with tetrahedrons. So I'm going to go File, Save Mesh, and I've already done this, so I'm going to replace the file that's there. Okay, so I'll go back into Solaria, and I'll go File, Import Geometry, down to Gmesh Mesh. Now, when I hit the Mesh button in Gmesh, it actually created 3D elements as well as 2D elements. The 2D elements were on all the surfaces of the 3D elements, but I don't need those. I don't want to import them, so I'm going to uncheck that. So I just import the 3D tetrahedron elements. So I'll hit the Import button, select that file that was just created, and hit Open. Okay, so here it is. If I swing it around, I can turn on the mesh, and there's the exact model that was just created. Now, if I look at the XY view here, I'll notice down the bottom here, when I move my mouse around, it tells me coordinates. And the coordinates are like 105, and down here it's a minus 115, okay? Which tells me the step file was in centimeters, or millimeters rather. So what I need to do is I got to convert this to inches. And to do that, I just go edit scale, okay? And I'm going to type in 0.03937, okay, which is 1/25.4 millimeters per inch. I'm going to hit select, and then I'm just going to box everything in. So all it's doing is essentially multiplying, adjusting each node location by that factor. So the model, it looks exactly the same, but now the dimensions are in inches. Okay. Now you can see I keep on sweeping around to this view here. So what I can do is I can go view, save view, and I can say 3D. I can save it for later on. Okay. So now what I want to do is I'm going to, this chassis here gets bolted to a heat sink. Okay. So what I'm going to do is I'm going to add interface elements. And by doing that, I'm going to extrude existing surfaces. So the bottom surfaces of these tetrahedron elements, I want to extrude into interface element. An interface element is used to represent a contact interface. So I'll hit add. So I'm going to define a contact coefficient of 0.1 watts per square inch per degree C, and I'll call this interface contact. Okay, so that's all I need to do here. Okay, so now I have to select the bottom surfaces. Well, we have an option here. These are all different ways of selecting surfaces. So any dialog, anything in the software that, sorry, all these things popping up here. It will have anything for selecting surfaces. Will have all these options here. Okay, and what I'm going to do here is by getting surfaces, it found all the free surfaces in this model here. Okay, and I'm going through, and when I get to number 4, it highlighted the bottom of the box. Okay, so I'm going to, once it's highlighted, I'm going to hit process, and that created the interface elements. Okay, so I'm going to hit OK here. So next I want to do is look at the front view here, and I'm going to zoom in the bottom, and there's my interface elements. Okay, and I want to create boundary nodes on the bottom here. So I'll go add boundary node, and I can come over here and reference the same property, or I can create a new one, either way. So let me hit add property, and I'll hit contact interface, and I'll define my temperature here, 45 degrees. Okay, and I'll hit OK. Hopefully, I'm getting some comments about the screen freezing. Hopefully, most of you aren't having this issue. So I've defined our temperature. I'm going to hit select, and I'm going to box in these bottom nodes here, just like that. Okay. Now, the next thing I want to do is define what we call IntelliMesh surfaces. Now, this model here is all built with tetrahedrons, and the model that Celerity PCB creates is different elements in a different mesh completely. But I want the two to make thermal contact at the card guides. So they're going to be completely different meshes, but I want them to be thermally connected. We have a thing called IntelliMesh. So if I go to add IntelliMesh, and what you do is you define master surfaces and slave surfaces. Now I'll talk about the slave surfaces when I get back into Celerity PCB. What we're going to do here is, again, hit our Get Surfaces button, okay? and we want to select surfaces on the card guides, okay, to define them as master surfaces. So if I, again, what I'm doing is I'm clicking on this here, this drop down. I can drop it down and select surfaces, okay? Or I can use my arrow keys on the keyboard. And that's what I'm doing. I'm hitting the down arrow key until I see the surface I want highlighted, which is, this is one of them. And then I'll hit process, okay? Oops, sorry. And I'll continue that. Continue hitting the down key. You can see all the different surfaces get highlighted. And now this one here got highlighted. So I'll hit process again. And I'll continue the hitting the down arrow. And then this one got highlighted. So I'll hit process. And you can see my count goes up each time. And I'll continue until this one gets highlighted, which it just did. And I'll hit process again. And I'll hit OK. I'm done. So if you want to make sure that you got them all correctly, what I can do is I can turn off everything except for this type of element and refresh the screen. So there's my 4 sets of IntelliMesh surfaces. Okay. And what I'm going to do is I'm going to save the model. And you can see I've already done this once, so I'll just save it right over that one. Okay. And what else I'm going to do is I'm going to define a group. Okay. Solari has 256 different groups you can have, and I'm going to call this one chassis. Okay, I'm going to do it just by boxing in the whole model here. Okay. And you'll see why I'm doing this in just a little bit. So let me go back to Solaria PCB and back to our board here. And I'll click on wireframe. And I'm going to go back into where we define that wedge lock edge. Okay. Before we we said one side was at 60 and one side was at 50. Well, now I want to disable that. So when I disable defining the edge temperatures, what it's going to automatically do, it'll create the interface elements. And instead of making boundary nodes, it's going to create slave IntelliMesh surfaces. Okay. And those are the surfaces that I'll want to mate with the ones in the box I just created. Okay. So I'll just hit OK, and I'm just going to go in, except one thing I'm going to do first is I'm going to go to PCB settings. This is where you define some settings some information that is needed that wasn't in the ODB++ file. For instance, the plating thickness of the vias and the material of the plating. Thermal information. I want to export this one as typical dissipations. So when you define the dissipation of a component, you have the option of you can define a typical dissipation and a maximum. So in this simulation, I want to do it based on the typical. The geometry, okay, the way it calculates the thermal resistance from the case of the component down to the board, this defines how you want to calculate it based on the minimum geometry, the maximum geometry, the average geometry, the average between max and min, or worst case. Worst case would be for a leaded part, the longest lead length, the shortest lead width, and the shortest lead height, resulting in the highest possible thermal resistance for that component. Okay, so I'm going to hit OK. Well, let me just go in here first. This is some meshing constraints where you can come in here and influence the overall mesh. We're going to leave it as the maximum edge length of one of those triangles as 1/4 of an inch. Okay, so what I'm going to do is I'm going to go back and build the board, and you'll notice that this dialog comes up now, and it's warning you that there's already a Solaria model in the Solaria window. Okay, and that's the chassis. So it's going through the same process as before. And again, it's going through the 6,552 triangles that were meshed that we saw earlier. And each triangle, again, this is for layer 1. It's processing each triangle to see if there's metal on that layer at the location of that particular triangle. And if you notice that in some places on your traces, on your layers, there's splits. There's areas where there's splits in the copper. And this is because one area may be at 3 volts and another area may be at 5 volts. But what a split will do thermally is it makes a thermal disconnect when you're trying to conduct the heat to the edge of the board. And all of that is accounted for in the simulation. But not only does it account for all the vias and all the shapes of all the signals and the traces and everything, but it's accounting for all these split planes in the ground, in the power layers. Okay, so we're just about done here. It's processing all the vias. Now, instead of leaving it 0, 0, 0, I'm going to enter an X offset of 20 inches. Okay, and this is so when the board is built in the Solaria model, it doesn't get plastered right on top of the chassis model. Okay, so we're done here. It says done. I'm going to hit cancel and go back into Solaria, and there's my chassis and there's my board. Okay, so if we go into group and then echo, you can see that it automatically put the board I just brought into its own group. So I have 2 groups, one called chassis and one called PCB. So this is the PCB. So now my challenge is to move this board so it mates up with these surfaces here. Okay, now this one goes to the top, and so it's got to be rotated 90 degrees, and then it's got to be translated 3-dimensionally. You see it doesn't line up or anything. So normally it would be a tedious process to do that, but we have a new feature called modify auto move objects. Okay, so I'm going to define my fixed group. So this is why I define groups. My fixed group is, I'm going to call them my chassis, and the moving one is my printed circuit board here. So I'm going to move the printed circuit board into the chassis. And I'm going to hit create groups. And what that did was it went through all the IntelliMesh surfaces, the ones on the board and the ones in the chassis, and gave them names. Okay. And you can see they're different colors because some are master surfaces in the chassis and some are slave surfaces on the board. Okay, so on the moving side, which is the board, I'll select my number 5 and number 6. Okay, and I want the then I want 5 here, okay, to meet up with number 3 over here. So I'll select 3 here, and then the other side, 6, will go to 4 down here, okay? So I want this one to line up with this, and I want this to line up with this. And I just hit move objects. Okay, and that's it. Okay, so there's my board inside my box. Okay, so all I have to do now is hit the solve button. And now I'm solving for the whole system. Okay, now one thing you'll see it exploded, and I've done this demonstration to myself a dozen times, and 11 of them I forgot one step. And I've got my little cheat sheet here, and I forgot it as well. I didn't define a material. When I brought in my step file of my box, I didn't define a material, okay? So I'm gonna come over here, and I've got aluminum, so I'm gonna define aluminum for my chassis. Okay, I know it's this one here, it's property number 1 because it's green, okay? So now if I go back into my solver and start it again, so now, again, it's solving the whole system. Our boundary conditions are the bottom of the chassis, okay, and our heat's being dissipated on the board. We've got 22.08 watts in the model here. And so it's solving the whole system together. Okay. So you can see it's done. So now we can just look at temperatures, and there we go. Okay. So there we're looking at, temperatures of the chassis and the temperatures of the board. Okay. So again, we can go back into results, PCB results, and look at our results in here. We can click on this, okay, bring up our group of our PC board, look at our XY view, and there's our temperatures. Turn off the mesh, and there they are. So each little square, this is the case temperature, and then the center is the junction temperature. Okay. So now what I want to do is let me continue. Okay. And I'll go group echo all to bring everything back. And I'll hit my saved view. And let me go back into Solaria PCB. Okay. So what I want to do now is I'm going to go back into our settings and change it to maximum dissipation. Okay. So I'm going to put another board right next to this one. Okay, in the other card slot, except it's going to have the maximum dissipation. So that could be the same board, or it could be a completely different board. But this is the process you'd go through to add, multiple boards into a chassis. Okay, the chassis could have built by bringing in a step file like we did here. Solaria interfaces, you can bring in models from ANSYS, you can bring it in from Nastran, FEMAP. We also support interfacing with the GMesh software, which is a shareware you can get free on the internet. And there's another one called NetGen, which is again a free 3D auto mesher that you can get from the internet, and that Solaria supports all of those. So you can, in addition to bringing in, geometry from external sources, it's a complete preprocessor as well. You can build your complete chassis model right in Solaria. Okay, so we're just about done here. And process the vias. And again, I'm going to put in my 20-inch offset. And it's cleaning up the model, sending it over to Solaria, and be done in just a second. And we're all set. So let's go back in here and look at again, we have our chassis, which has one board in it, and now we want to put this one in the other card guide. So we'll go through the same process. Auto move, so our chassis, and now we're going to select PCB_1. It recognized that it was already a group with the same name, so it gave it a different name. So I'll hit create groups again, and again, just like before, 5 and 6, except this one here, I want the 5 to go to 2, and I want the 6 to go to 1. And I'll hit move objects. Okay, so that's it. And just a matter of just solving again. And now we're solving it for the left board is at typical power dissipation, the right board is at maximum dissipation. So we should see, different temperatures just based on that, plus the non-uniform contour of the chassis itself. Okay. Again, we have two solvers, a finite difference solver and and they both have steady state and transient capabilities. This one here is the GCG solver. Sometimes they solve quicker using the finite difference. Sometimes they solve quicker using the GCG solver. So it's just a matter of trying one versus the other. they're both going to get to this exact same answer, because what it does is once it meets the convergence criteria, whether it's this solver or the other solver, it starts doing a heat balance. And when it meets the heat balance criteria, that's when it says, I'm done. Okay. So there we go. There's our two boards in here. Again, we can go into results, PCB results. Okay, we can turn this off. We can look at, and so now we can look at both boards. So there's the second board we brought in, and there's the first board. In this one here, it's 2.3 watts at 96 degrees, and the other board is 2.6 watts at 101.5 degrees. Okay, then all this information can be saved to a text file, or bringing it into Excel, or bringing it to a report, or something like that. I can clean up the screen by turning off things by element type, just to make the view a little bit cleaner, things like that. So there's a lot of capabilities in the software. Okay. So any questions on that? We have about 5 minutes. So what I'm going to do is I'm going to go to a PowerPoint presentation. One of the things that when we're talking about components, we were just putting in like a junction to case resistance, a very simple representation. But Celeria's PCB can handle more complex representations like a Delphi compact thermal model. Here we have an example of one which shows a matrix of the resistors and the nodes they're connected to. There's a bottom inner and a bottom outer, and there's a side node, and there's a top inner and top outer. Okay, so in Celeria PCB, you define your nodes, so junction and all these nodes here, you define your nodes, and then you just define the resistors, just like it says in the table. You've got a junction to top inner with 0.02. So you'd select your junction node, you'd select your top inner node, and you'd give it the value of 0.02. And in Celeria, after creating the Celeria model, it's exactly going to duplicate this resistor network that you've defined. Okay, it'll put the heat load into the junction. It'll create in the mesh of the board, it'll create an inner area and an outer area, and the bottom inner and the bottom outer will be thermally connected to those two different areas. When I talked about before about splits in the planes, we got a customer sent us this image here, and they said there's got to be something wrong. We see these very weird temperature profiles in our board surface. You can see these blocks of sort of isothermal with these big sharp temperature gradients. Okay, so we figured you contact Harley Thermal because there's got to be a bug in the software. Well, fortunately, he was able to send us the Celeria PCB file, and we looked at the different layers. We saw these blocks of copper. Okay, and we looked at lots of the layers, and they were all identical. Okay, and when we looked even closer, in this area, there's these splits. Again, they're at different voltages, so they create these splits. But the unique thing about it is all the different layers, all the splits were right on top of each other. They were all identical. And to get the heat from here to here, you've got to conduct across 25 mils of plastic. Okay, and because they're lined up, if the metal doesn't overlap on different layers, it's going to create this thermal resistance between here. Okay, if they shifted one of them or every other one by 100 mils or 200 mils, then you'd create a conductive path across it. But they didn't, the electrical engineers. So if you lay the artwork over the temperature contour, you'll see the reason for these areas of these sharp gradients. Okay, so we're looking at peak temperatures of 141 degrees. Well, in Celeria PCB, you can, in that layer dialog we're looking at, you can come down here and check coverage. And by checking coverage, it tells it to ignore the traces on that layer. And what I did was I went through for each one, looked at the artwork, and I said, well, that's a signal layer, so it's about 20% copper. So it's using this smearing methodology to, instead of accounting for the specific traces, it smears it over the entire layer. So 80% for this layer, 80%, 25, and so on and so forth. And then I solved it. And you can see the significant difference between using this smearing methodology, which is a very common way of doing it because, you know, you don't usually have all that information to go to that fidelity. So you can see one prediction says your board failed and one prediction says your board succeeded. So you can see it's important to capture those kind of details when you're depending on the board as a conductive path to your heat sinks. So it's important again when you're depending on this. So I'm still getting people saying that the page is freeze. Hopefully we'll be able to record it and that presentation and show it later on. So we're at the end of our presentation. If you have any other, I'm looking at your questions here. Let me see, can your software be used to simulate in air in a vacuum? And the answer is yes. If we go into Solaria PCB and go into PCB settings, under thermal, there's a thing that says space environment, okay? So if we check that, now I was talking about how Solaria, Solaria PCB, when it creates a Solaria model, it calculates the thermal resistance between the case node and the board surface. Well, part of that resistance, when you have a board sitting in atmosphere, is gaseous conduction under that gap underneath the component. Well, and Solaria accounts for that gaseous conduction in calculating that resistance. If you check this here, then that is neglected. It's assuming there's no heat transfer, there's no air in that space. So that's the answer to that, and it'll simulate that vacuum condition. Okay. Are there any other questions at all? If you do have any other questions, there's a place you can email to TFAWS and they'll send them to me and I can ask. If you go to solariathermal.com, you can request a demonstration. The software is relatively inexpensive. For Solaria and Solaria PCB, it's a purchase for $10,000. Again, you own it and includes a year of software updates and support. And you'll get support from someone like myself who's been doing this for, I hate to say it, for almost 40 years now. So again, I appreciate TFAWS for being able to conduct this virtual environment in these troubled times. But it's fortunate that they were able to do it and continue TFAWS virtually. So we're very glad. And then again, thank you for